Example 2. A culture of bacteria obeys the law of uninhibited growth. Part A. If n is the number of bacteria in the culture and t is the time in hours, express n as a function of t. So in this problem, we're asked to actually come up with the model rather than just using a model that's given. So we know our general form of our exponential growth and decay models is A sub t equals A sub 0 times e to the kt. So a of t equals a sub 0 times e to the kt. So remember, this is your generic a, the amount of a substance. Well, in this specific example, we want n to be the number of bacteria. So we're going to use n instead of a. So our function would be n of t equals n sub 0 times e to the kt. Okay, now in part B, if 500 bacteria are present initially, and there are 800 after 1 hour, how many will be present in the culture after 5 hours? So in part A, we just made this generic form of our function, but now we have to actually substitute in some values here. So our only variable is t, so we've got to substitute in the n sub 0 and that k. So we have 500 bacteria present initially, so we know that our n sub 0 is going to be 500. But now, as far as that k, we're going to have to actually solve for that. So we're going to use the information that we're given, 800 after 1 hour, with the 500 present initially, to find that k. So we know our time is 1 hour, t is equal to 1, our n sub 0 is 500. We have to find that k, and then we're also given that 800, so we're given that number of bacteria after 1 hour is 800. So we're going to substitute in to our function here, and we're going to substitute in for everything except k. So we're going to have our n of 1, our n of t will be n of 1, which is 800, equals our original amount, our n sub 0, which is 500, times e to the k times 1, our time of 1. So now, if I want to solve for this k, I'm going to have to isolate k, or get k out of that exponent. But first, remember, we've got to isolate the term that contains that k. So that e to the k, I've got to get rid of this 500 here first. So I'm going to divide both sides by 500. So I'm going to have 1.6 equals e to the k. Now, we can use logarithms to rewrite this without that variable in the exponent. So we'll rewrite it using the definition of a logarithm. So natural log of 1.6 will equal k. So we can now substitute this natural log 1.6 into our function for our k. So we can say n of t is going to equal n sub 0, the 500, times e to the natural log of 1.6 t, and I'm going to move the t into the front so they don't get confused and accidentally multiply that 1.6 times t. It's t times the natural log of 1.6. So we can now use this function to solve for what they're asking, which is how many bacteria will be present in the culture after 5 hours. So we'll just now use this function and substitute in there a t of 5. So we want to find n of 5, so 500 times e to the 5 times natural log 1.6. So we can enter into the calculator 500 times e to the power 5 natural log 1.6. So see, they're prompting you with another set of parentheses around the 1.6, the argument of the log, and then you've got to close those total parentheses around that entire exponent. So that's going to give us about 5,243. We'll round up, can't have a part of a bacteria. We'll round that up to 5,243 bacteria. So this is approximately 5,243 bacteria in the culture after 5 hours. Now part C, they want to know how long is it until there are 20,000 bacteria. So we have our function from the previous page, so we have our n of t equal to 500 times e to the t natural log 1.6. So we want to solve for time here, and we're substituting in our n of t, the amount after so much time, is 20,000. So this is our n. So we'll just substitute in 20,000 equals 500 times e to the t natural log 1.6. And then I'll let you guys finish the rest of that on your own. And you can check the solutions on Blackboard.